Hello everyone. So my name is Apurva Mishra, and I am a software programmer from 1678, and I will be presenting to you all about auto development on Citrus circuits. So just before we get started, who am I? My name is Apurva Mishra. I am a four-year member of 1678 and a Citrus service programmer last year for the St. Louis Regional and before that. Additionally, I lead new programmer training on our team for robot programming. And yeah, that's a bit about me. A quick outline of today's presentation. We will be going over, what is an autonomous program? What exactly constitutes an autonomous program, right? How do we get started with auto development on 1678? What are the things we think about? What are different factors involved? And then from there, I'll go into how we actually develop a plan for how we want to create our autos, what autos we want to create, and different planning processes. And then I'll finally go over what actually we do on 1678 to write our autos and execute upon them so then they are ready at competition. And at the end, I will have some resources for you all if you would like to use them. All right, so what is an autonomous program, right? That is the first question to obviously ask when we discuss auto development. Autos in FRC are basically where the robot moves without any external control. You don't have any driver, you don't have any operator. It is simply what you program on the robot, right? To make it complete your point objectives in those first 15 seconds of an FRC match, right? That means that throughout this entire time, throughout this 15-second period, you are entirely reliant upon sensors, right? You're reliant upon, your encoders, your gyro, your vision tracking sensor, right? Etc. And a really important part of autos in FRC is obviously that you have to automate all your tasks, right? You can't have the operator do something even as simple as intaking the ball. You have to code away and time away for the robot to do that at a specific point in time during those 15 seconds. So today, over the course of this presentation, we'll be going over a couple of things that makes a good auto robust as it is, right? Makes it effective in competition, right? And there's multiple things that constitute this. For one, we want our robot to be robust. This means that we want our auto to be not only effective, but we want to make sure it's consistent, that it will work many times, right? It'll work as many times as we need it to, and we can rely on it consistently, right? Of course, we also want to make sure that our auto is good enough for time, right? We want to make sure that our auto will work within those 15 seconds, and we want to thus make it time efficient as possible. We want to make sure that it moves as fast as possible and that we can get everything we want to get done in that time, right? This obviously means that our auto needs to be efficient. But something that's important to think about is that not only should your auto be time efficient, right? To get as many tasks done, right? To get tasks done as fast as possible. If you're intaking the ball, how can you do that in the fastest way possible? But also efficient in the point objectives we actually complete, right? Like, what do we hope to get done in our auto? And what are some of the trade-offs between scoring points and making our auto more efficient, right? And there's a lot of factors that are going to be involved in that because there's a variety of situations that will be discussed in the presentation that affect this efficiency in the auto between scoring well and making it time efficient to get done what you need to for the rest of the teleoperated period in the match. And then finally, we will be discussing, how to actually get the highest amount of points as possible, right? Because in the end, that's what you hope to do in your auto. You hope to set yourself up really well for the rest of the 2 minutes and 15 seconds that you will have in your game. So I think this is probably the most easy way to think of the pathway for creating an auto, right? We have discussion, right, and formulation of the auto we want to create, right? This involves, a lot of brainstorming, a lot of, like situational thinking, right? And then after we come up with the autos we want to code, right, we will execute upon that, right? That's when you actually code the auto. That's when you actually make it as time efficient as possible, etc. And then before competition, perhaps I would argue, like one of the most important things is that you make sure that your auto is completely reliable, right? That you test it enough times that you know it will be consistent, that you know that in competition, if something goes wrong, you know where you can fix it, and how to make sure that your auto won't work just one time, but it will work many times, right? And that is the step process that I will discuss as we go through the presentation today. So how does plan development work on 1678? The first thing that we do on 1678 is that we develop point objectives, right? One of the most important things in understanding what the best auto to create is just understanding like the game itself, right? Understanding the differences between point scoring and auto versus teleop, right? Understanding the differences between the ranking points that you can gain from things in auto versus teleop, etc., right? So in case of 2020, last year's game, right? You know that you had 5 points for crossing this initiation line, right? And that the point value was doubled for power cells no matter where you scored it. You also knew that you had a 15-second time limit, and that the match allowed you to start with 3 power cells at the beginning of your auto. And while you didn't need to, this was an option, right? So being able to understand these things is really fundamental for understanding the strategy you can involve in your auto development. So after we develop our point objectives, our strategy subteam creates an auto draft, right? So what I mean by an auto draft is that we basically discuss a lot of the point objectives that we hope to actually complete within our match, right? This means that we have to observe what are possible openings, right? For places in our auto where we have opportunity and how to make the most of those opportunities to score as best as we can. I remember in our discussion in 2020, one of the biggest things we discussed was whether we would like to focus on a robot that started from the right, that took these 2 balls here, right, these 2 power cells, or whether we'd want to start from the left and take all these 3 that were in our zone, right, and use it from there. So these types of situations are the things that we usually discuss with strategy, right? Because you want to make sure that you can get the highest point score as like the highest point score possible for your robot. At the same time, you have to consider the limitations of your robot, right? Like there are trade-offs, like, do you want to score in the high goal, right? Or do you want to score in the low goal? Where do you want to intake from exactly? Do you want to intake from these bar cells or not, right? These are all things that you need to think about. And lastly, once you've developed these point objectives for where you think is the best to intake from, right? Where you think, like what you hope to do, whether you hope to score in the high goal or the low goal, you have to map your paths, right? Here's an example of one path that we mapped. We thought that we would intake these 3 balls, right? And quickly turn around to intake these 2 before ending right in front of the goal, and then shoot from the high goal from here, right? This was one path that we came up with. The important thing about path mapping is that you want to make sure that your auto is as efficient as possible, right? And at the same time, you want to get the maximum amount of points as possible, right? So for example, one of the options last year, right, was that we could intake these 3 balls, right? And then we could intake these 2 and shoot, right? And this would mean that we didn't include the 3 power cells at the beginning. And then we could drive over to these 3, right? And then shoot them. Or what we could do is that we could start with 3 balls, right? And perhaps intake these 2 and then shoot those before going on to another 3 power cells, right? So it's really important to have these kinds of discussions with your team, because everybody has these different perspectives to bring to the table, right? Something that you may think of, right? Somebody else probably has not thought of, right? We're all still figuring out the game and abilities, and we're also figuring out exactly how we need to get going with our paths. And so having a large group discussion and brainstorming exactly what the best way is to complete this auto while we bring multiple viewpoints to the table is really important in the discussion that goes into auto development. So something that's really important in auto development overall that is especially focused on in the discussion is how do we bring in variance and flexibility within our autos, right? Because like even last year, right? Something that 1678 aimed to do was come up with a 10 power cell auto, right? But we also realized that, it wouldn't always be probable that we get to use just this one auto, right? So in order to take care of these multiple situations, we had to come up with multiple paths. So we came up with a path to do an auto from the right side, to do an auto from the left side. And I'll bring up a couple situations, a couple case studies in a second, but these things really, altered the way we went about auto development because we wanted to make sure we covered as many contingencies as possible. And an FRC match, there are lots of things that are variable, right? You may have different alliance partners, you may have different point objectives for where you're standing in the game as a whole at the moment, right? And these things all need to be accounted for when you come up with your autos to make sure that you cover the highest number of situations possible. Of course, something really important to think about while you do this though is, what is the best use of your time? Because it's not always the smartest idea to cover every single situation possible, right? Every single auto that you on your team dedicate yourselves to working on, right? That is an auto that is going to take a lot of time to perfect and make sure that it is reliable in competition, right? So you only want to work on the autos that will have the highest impact, that you can keep consistent and are most important to cover, right? There are lots of corner cases that you could come up with, but it's important to filter these out in the discussion to only come up with, I would say, 3 or 4 autos that you think may suit your robot best. So a really good example of situational thinking to come up with multiple autos is quals versus elims in 2018. So for anybody who doesn't quite remember, in 2018, this is how the game map looked like. You had these cubes, right? And these cubes would basically be used to stack onto either the switch or the scale. And depending on whether your cubes weighed the scale down onto your side or not, you would earn points on a time basis. And this was really important in our auto decision making for a variety of reasons. But one of the most important things that we came up with was the importance of ranking points within the 2018 game. Because for 1678, that clearly defined the difference in our auto for qualification matches versus our autos for elimination matches. So something that we first thought of was that in qualification matches, right, you had to be self-reliant to control the switch and the scale. Now, the reason I talk about this is that in 2018, you would gain a ranking point for having all 3 of your alliance members cross this auto line. You would also get a ranking point for having control of your side of the switch, right? And something else really important to think about is that the way you got started with your auto on controlling the scale was extremely important for the dynamics of the rest of the match. Because again, scoring in 2018 was based on a time thing, right? That for however long you had possession of the skill, that's for that time period is how many points you scored. And so, coming up with a balance between these two things and qualifications versus elims is something that went into a lot of the discussion on our team. One of the most important things in qualifications that we realized was that no matter what, we had to gain the ranking point that you would get from controlling the switch, from your side of the switch, right? We knew that, in a good match, we would have all 3 of our all 3 alliance members cross the initiation line, and we would get our auto point for that. But in qualification matches, you also don't know who you're going to be paired up with, right? And because of this, on our team, we come up with a lot of, auto impact situations, right? You may be with teams that are, really useful for the match, but may not have the most effective auto for the specific situation that you've come up with, right? And because of this, we thought in 2018 that no matter what, it was very important that we always filled at least 1 cube in the switch before we moved onto the scale. In elims, however, it's important to recognize that you get to choose, or at least who your alliance partners are going to be. That means you know their skill sets. That means you know what they can contribute and what they can't, right? And that means you also know exactly how you can collaborate with them throughout playoffs, right? So because of this, a lot of the stuff that our team did is that for elimination matches is that we simply focus on point scoring, because in qualifications, you have to be concerned with, actually gaining those ranking points. But in our elimination matches, we understood that our first or second alliance member would be able to fill, that 1 or 2 cubes on the switch, whereas we could focus on the scale to make sure that we maintained possession of it for the rest of the match. And of course, that was really important in 2018, again, because early possession was always helpful in maintaining the dynamics between point scoring over time. It's important to realize that, these types of situations come up in many different years, right? In 2019, you gained a ranking point for filling a rocket, right, completely. And something that our team came up with in 2019 then was that in elimination matches, we realized that it was a much smarter idea to get the 2 panels, right? To have the 2 hatch panels scored on the backside of the rocket that we couldn't see. So that way we wouldn't be stopped by defense by a robot from the other team who might be free during elimination matches and focused on defending us, right? So these types of situations come up a lot. And that is, again, why it's extremely important to have such discussion on your team, to come up with these different perspectives and try to understand all these different cases, all these different contingencies that could affect your auto development. So, bringing the discussion to what 1678 thought about last year, right? I wanted to do a case study about our 8-ball auto. I'm going to play a video here of our 8-ball auto at the Los Angeles North Regional. And then we'll go into a bit of discussion on what was the thought process for coming up with this auto and executing this auto at this time. This is our robot right here. And here we've scored 5, and now we picked up 3 more, and we scored those next 3 before moving on in the teleoperated period. So there were multiple different situations that we had to think about when coming up with this auto. One of the first things that we had to actually think about was whether we wanted to go with an 8-ball or a 10-ball auto. This match is from the first qualification match we had. Sorry, not qualification, first playoff match that we had. This was quarters 1 in LA North. And we decided that we would go with the 8-ball auto because we knew that our alliance members would be able to contribute as well and have their own effective autos, right? The 10-ball auto that we had, we knew would take up space on the field, that it might restrict the auto paths of other alliance members. And so because of that, we knew that it was important to go with our 8-ball auto. At the same time, it's important to recognize that some of your autos will have strengths and others will have weaknesses. For us, the 8-ball auto was extremely consistent and worked well, which is why we decided that it would be safer to play with it in elimination matches. But in actually developing the auto, we had a lot of different situations to also think about, right? And another one was this idea, again, of whether we wanted to start on the right side or the left side. Something that we had thought about was that if we started on the left side, right, we would be able to intake balls that were in our safe zone. right, in our trench. But we wouldn't be able to intake balls that the opposite alliance could get. So we decided that if we start on the right side and we intake these balls that were close to us, then we could easily score 5 before moving on to intake the next 3, right? And because of this, we thought that our right side auto would be the best auto to play here. At the same time, it's also important to collaborate with your alliance members to understand that they may have an auto that might work on the left side. For us, that was true, that was the case. But in the case that there wasn't a strong left side auto, right, and we wanted to have effective scoring from the left side, then we might create a left side auto in order to do that. But one of the most interesting points that I think comes up in a case study regarding our decision making for this auto was the topic of having a far versus near auto. In the 2020 season, we actually came up with 4 8-ball autos. We came up with an 8-ball auto to do from the right side, an 8-ball auto to do from the left side. But for each side, we also decided to do an auto that would score from the far side and the near side. By the far side, I mean that we would, far meaning that we scored from around, the actual pillar here, right? Whereas the near side auto was basically where we scored from right in front of the goal. The reason we did this was to leave space directly in the center here. Because when you leave that space directly in the center, you allow movement for your alliance members. I remember in this match specifically, we wanted to make space for our alliance so that they could score from their scoring position, right? And so in order to collaborate with them and to make sure that our autos didn't interfere, we had this far versus near side auto to avoid that middle space and avoid any problems that you could have, because that does indeed occur, in a match where you're moving across the field to do your auto, right? And yeah, these are all important things to think about, and they go into the discussion of auto development on our team. Sorry. So now we get into actually creating our autos. So to create our autos on 1678, we have to identify common point locations. This means that we build off of a general auto to make multiple versions that we can use throughout the season. As I discussed, in this last example, we had 4 autos, right? We had 2 right side autos and 2 left side autos. Of course, however, the intaking for both sides was going to be the same. Some of the point locations for intaking the next 3 balls was also going to be the same. The only difference we actually had was the position of shooting that we had for the autos, right? So in order to come up with consistent autos and to make sure that they were robust and they worked well, we had to simply identify these common point locations. And I'll discuss this, in a bit, but we use something called odometry to basically, understand what points on the map, right, we want to target, right? And then we created trajectories with those points that we can use for our auto. So now, what are trajectories and actions? Trajectories and actions are what we actually use to organize and code our autos. Every time we create an auto, we come up with these different point locations that we've identified, right? You might have an intake pose, you might have a second intake pose, you might have a near shot pose and a far shot pose, right? But to actually create, a path between these, you take this trajectory, right? You take these points that you're going to have on your auto path, and you put it through the trajectory generator. Now, our trajectory generator is essentially something that calculates a quartic Hermite spline, and that creates a path for our auto that we can use. Just for the audience's reference, you can use the WPI lib characterization and path viewing tool. We just use a slightly customized version of that uses a quartic Hermite spline as compared to WPI lib's calculation. But besides that, you can use that path viewing to create your trajectories. And once we've calculated our paths by putting these point locations through, we come up with actions. And actions are essentially, the auto paths that we give our robot the command to run. And running each action thus effectively runs our auto, or at least runs the parts of the auto that make it work together. So in order to effectively code autos on our team, we group our positions, right? So something really important to recognize is that readability in auto code is extremely important. There are many different positions that you need to take care of. There are many different paths that are slightly similar, but have slight variation. And most importantly, you want to be able to identify errors and where the errors are present, right? You want to be able to effectively pinpoint the problem and then address the problem immediately. So you can, have more effective and efficient auto development, and you can also, be safe, right? So because of this, a lot of our auto coding comes in organization, right? So here's an example of some of the organization that we had for our autos. These are all post 2Ds, which are basically, points that have a direction, right? They're vectors that we create. And we basically have a starting pose, right? A shot pose and an intake pose. And in fact, a lot of these positions are quite similar, but they're quite similar to each other, but only different in the sense that, they might start on the left side or the right side. But to maintain this sort of symmetry, right, we name them similarly, which is why we have, R stands for right and L stands for left. And we have these shot poses, intake poses, etc. Right? This allows greater readability. This makes sure that we know what positions are going through our trajectory generator when we produce our actions. And this also means that we can effectively, group the different paths in our auto to code it the best way possible, right? So you might group the points that go into the first intake, right? Then you might group the points that go into, shooting, and then you might lastly group the points that go into your second set of intaking before you shoot. Something important to also think about in code readability in general, and this is something that our team does always, is that you want to work with units that are, easily understandable, right? You want to work with units that you can understand, that you can have an easier time with to pinpoint problems and fix them, right? And this comes really handy, and this is really important when you actually, work with unit conversions, when you have to work with odometry, because on our team, right, encoders are measured in ticks, right? We have angles that are measured in radians, right? But in order to have a greater understanding, something that we always do is that we always convert our radians to degrees, so it's better understood, and we convert our ticks to inches. And that way we can understand, if the encoder has moved this many ticks, how many inches has a robot moved? And that is obviously more understandable for any debugging that we do with our auto. So now we get into perhaps one of the most important parts of programming an auto effectively as a whole. And this is the idea of robot odometry. Robot odometry is simply knowing where you are in relation to the field, right? Or in relation to your robot. It's using the sensors on your robot to understand your position, understand your heading, which is your angle, and use that to come up with the most efficient and effective path possible, right? We use odometry when we create our splines, and it's really great when we also do our path viewing that you can see here, right? So why is robot odometry so useful? Robot odometry is basically the idea that suppose my reference point on the field is the center right here, right? Then my robot will be perhaps 140 inches and 80 inches to start here, right? And you basically, need this sort of, path tracking. You need this location tracking to understand where your robot is and going to be. So odometry would be knowing that you are at this point and that moving this number of ticks means that you've moved to this new coordinate. And that is something that your robot can keep track of, right? And that is what odometry is. Why is odometry, so important to think about when you create your auto, besides, just understanding, like moving from one point to the next? There's times when you want to actually reset the odometry of your robot. This is because in an auto, right, we have this visualizer here that explains, what path our robot is really going to take, right? That it should take this pretty nice S-curve to stand here and then shoot. But oftentimes, this isn't exactly the way it works out in real life, right? Your robot may accumulate error, right? Your encoders may accumulate error due to friction from the rug, from something else. And so you don't want to have your error accounted into the position when you create a trajectory, because that would effectively mislead your robot to thinking that it's perhaps farther than it actually is or closer than it actually is, when you want to, just tell it to move a certain amount of inches forward, right? And so that complication is why it's sometimes important to reset your odometry, and to, so you can make sure that you're not accumulating this error as you go through your auto. And again, if you have any questions throughout this presentation, please feel free to ask. I would love to answer. Visualizing is really important to have when you're predicting a path, right, to create this framework. And this is really important not only for auto efficiency, but safety, right? We use, again, just a slight variation on the WPI-lib visualizer that there is for autos, right? And this visualizing is really important because it helps us understand, very simple things even about our path, right? For example, you have differences in heading, right? That you may need to account for, right? Like last year, something that was very confusing for us was understanding whether here our robot was to be at a heading of 180 degrees or 0 degrees, because we were intaking a certain way, and then we needed to obviously move, if we intake forwards, then going back here, we don't want to turn the robot 360 degrees to drive forwards to get to here, right? We would rather that it maintain this forward position and simply drive backwards to here, where we can then have our turret shoot, right? So having a visualizer to, understand the heading of your robot this way, right? And understand, just how far your robot is going is something that can be really important for creating an effective auto, right? And making a good use of your time while you're in the shop and outside of the shop, so that when you test your autos and you take the field, you are prepared and you can be efficient with any debugging that you need to do. So, while these coding practices are really useful, right? We want to, no matter what, always test our autos step by step. This is because, you might have a visualizer that tells you, the path that your auto should make, right? You might have code organization and you might, test every step of the auto separately, right? But if you make a change in your auto, right, you don't want that error, if you do cause an error in your change, to compile over throughout the entire course of the auto, right? You want to work on and pinpoint the single location in your auto that is, messing up your trajectory, right? And deal with that before moving on to the rest of your auto. In terms of safety, this is really important because you don't want your auto to move on into an unknown direction if you do make an error, right? So this is where, organization of code comes in really handy, because if you have your code organized into these different auto trajectories, right, these different point locations, then you can simply identify the problem area and only call on that problem area when you're running your auto, right? At the same time, if you test for every single change, then you know exactly where your error is occurring in the auto, and you can pinpoint that before moving on to the next error. And that will inevitably lead to greater efficiency when you do your auto development, because you will have a greater understanding of where your errors are and what they are, so you can fix them. And a last point to understand is that, again, we have a visualizer for our auto, right? But the changes on a viewer may not always be accurate in real life. This actually, ties back into drivetrain characterization as a whole, right? In past years, the settings that we used to have our viewing were actually like quite inaccurate for the actual auto paths that we created. Only this last year were the paths that we saw on our viewer quite similar to the actual auto paths that we ran. And the reason this is because you might have a unique gear ratio, right? You might be using separate wheels, right? There's all these physical constraints, right? The friction of the rug, right? These all may cause your robot to accumulate error, right? And that makes your auto different from the way it might be in a viewer. So being able to, again, test step by step in your auto development to work on only one part and make sure you know that one part works before going on to the next is very important for completing your auto and making sure it is reliable and consistent. So now we come on to, like a bit more of an interesting topic, because some of these variables might not be things that you can address immediately in your shop, right? But it's important to understand that there are lots of physical factors that could affect the auto path that you code, right? In your shop, you might have a different kind of carpeting, or you might have a more smooth or rugged carpeting, right? That could affect your auto path. We've discussed this before, but you may also have different alliance members, right? That could affect your auto path if you don't understand exactly where they're moving, or you don't collaborate with them and you don't communicate with them, right? In fact, in 2018, I believe, 254 came up with this very interesting case where they, understood that the Coulsons in 2018 would actually, slip or create or have more traction dependent on which side of the field you were on. This is because the field carpet was, more able to catch onto the Coulson wheels, right? The Coulson wheels were able to gain more traction to the carpet when it was facing one way as compared to the other. And because of that, 254 actually came up with a calculation of their own to account for this carpet friction and carpet drift. This kind of drift is also really important to take into account when you're trying to make your auto as fast as possible. Last year, when 1678 was trying to do our 10-ball auto, we were extremely pressed for time and making sure that we were able to score all 10 balls at, within the 15-second period, right? Having an understanding of where you might have, drift because you are accelerating very fast throughout a turn, right, would thus be really important to account in terms of error, because these things can affect your auto even if you think they may not. And so having an understanding of these factors is really important for developing an auto that will work. But at the same time, it's important to understand that if you set up and organize your code well, then there are situations that you may not be able to address in your shop that you can address before competition. I know that at the Los Angeles North Regional, for example, 1678 actually went through a couple of quick auto tuning changes to make sure that our autos were still consistent on the field. And one of the most interesting cases that we found was that the lighting in the venue actually caused our vision tuning to be different than the way it was in our shop, because there was sunlight in the venue, and that actually caused our vision tracking to be less effective and catch onto the target less, and even catch onto other metallic objects that reflected a green light back onto our turret, right? So we had to, throughout the testing, right, and practice matches, right, we actually we made sure to tune our vision in this way to account for the variables that we incurred going into competition at LA North because of the change in venue, right? And of course, it's important to recognize that you're taking your robot to a venue, right? You want to make sure that you test that your drive chain characterization, everything else works properly, that everything about your robot is well, right? So the same way you would check all the mechanism on your robot, you want to check your autos the same exact way, right? So I think auto development really brings in the important aspect of automating tasks as a whole, right? Task efficiency is something that 1678 really focuses on even throughout our teleoperated period, right? Because we want to make sure that the tasks that we know we have to complete in a match are robust as possible, right? So the example you see in this slide is our 2019 triple climb, right? So to kind of go through this process of this understanding of why we need to automate tasks, I'll discuss it in reference to this climb. So for our 2019 climb, right, something that the operator had to do was know what height to raise the robot to before driving it forward onto the podium, you could say, right? This is actually, this would be really difficult from the standpoint of a driver in the driver's station because, you're rushed for time, right? You may only have a matter of seconds left before the end of the match, right? And you need to take these two robots with you and, make sure you are at the correct height and you can accurately move forward without, causing any errors that would, maybe lead to some disastrous climb instead, right? So instead automating this task, right, instead of having our operator, manually reach the robot to a specific height is much more viable, right? It's something that we would much rather do for operator ease. And this is because if we automate the task, we can tell the robot to be raised to a very specific height to begin with, right? And we can say that the moment you reach this height, simply move forward. And because of that, the operator only needs to press, one or two buttons to do this climb, right? Instead of, God mode it the way they might originally, right? And automating tasks is again really important because not only does it allow for operator ease, but it may even, remove restrictions to tasks that your robot could complete because they might be inhumanely possible, right? In 2019, something that we did besides, this climb right here to automate tasks in a sense was that we had a button for vision tracking when we caught onto a target to place a hatch panel because something we realized was that placing a hatch panel on the far side of the rocket was a very difficult ordeal to do, especially under defense. And if you didn't place a hatch panel properly, then if you put in a cargo into the rocket, then both the hatch panel and cargo might fall, giving you a lot of point loss that you would rather not have. So by automating our vision tracking to the actual targets, we were able to, press a button that the robot would use to create a mini spline, you could say, and attach the panel to the target, as it found the vision target, right? And because of that, we were able to accurately place hatch panels, right? And more effectively go through the rest of the match without worrying about, accurately placing this panel, which would, take away time in our match because we were trying to line it up correctly, or, do something that might not even be possible if we were under defense. So, along with automating tasks, it's really important to discuss implementing control in general, right? On 1678, we implement control with PID integration, right? For any of you that may not know, PID stands for proportional integral derivative integration, right? And it's essentially a form of control that allows you to reach a goal in a stable manner so you don't have to oscillate and that you can reach your goal in time in the most efficient manner possible, right? You can see here in the plot to the side that our proportional gives us the actual power to reach our goal, right? But then our I and D terms are what allow us to take away this oscillation, right? And make sure we raise ourselves correctly to the goal so that we can, control our mechanism the best way possible. A really good example of where PID control is implemented is, in, for example, an elevator that you may have on the robot, right? Every time you want to raise your elevator to a certain height, right, there are things that you need to take care of, right? You need to take care of the effect of gravity when going up and down on the elevator, as well as simple oscillation that may occur from trying to quickly raise your elevator to a specific height, right? So PID takes care of this really well because you're able to, reach a certain objective, but the I and D terms make sure that, by accounting your velocity, which is the derivative term, right? And understanding the error that you have left in reaching your goal, the I term, you are able to, in the most effective way possible, create a curve that makes you reach your goal without having the elevator oscillate above and below the desired height, right? So this is really important, of course, because if your mechanism is oscillating, then it isn't the most efficient possible. And if it is also oscillating, then it won't be reliable, right? If you're trying to place a hatch panel while your elevator is oscillating a bit, then you'll have a much harder time scoring than if you had than if you implement PID, right? So you can implement your own custom control, right, with custom coefficients that may work best for your mechanism. But PID is also built into CTRE and Rev controllers. So if you don't want to have custom control, you can also use the PID control and integration that comes in to these controllers. So, now we come finally to the stage of being prepared. We've developed our auto, right? We went through the discussion, we went through all the different contingencies that we hope to, address at competition. We want to simply now be prepared to make sure that we can execute the auto that we've worked so hard to create over the season, right? So, the first part of being prepared for competition is, again, the idea of auto flexibility, right? We want to be compatible with other teams, and we, want to create multiple auto versions, right? We want to address all the situations possible and be prepared for, any shortcoming or any issue that we may incur throughout competition, right? If we realize that our left side auto isn't working, right, then, for example, it's really important to know that we still have a right side auto that will work, right? So being able to come up with these, backup autos, these, cases to create multiple auto versions is really important to be flexible throughout a competition, right? And again, different autos might be necessary for different matches too, right? You might realize that in a qualification match, you want to make sure that you score more points in a certain way or take away more intake opportunities from the other alliance, given the skill set of the other teams in auto, right? And this idea of score priority then obviously changes the autos that you plan to do at competition. So having the sort of flexibility can come in really handy to make sure that you aren't relying on only one or two autos that might, for some variable reason that you may not have thought of before, you don't want those to cause your autos to fail as a whole, so you don't have a viable auto to use on competition day. And again, you want to be ready for any anomaly that may occur in competition, right? Something that you have to think about is that in competition, the field may shift as compared to the practice field, right? And you want to make sure that your odometry works correctly in this regard, right? If you have a certain reference point on the field and for some reason that reference point has now changed going into competition, you want to make sure that your code is prepared for that so it can correctly recalculate trajectories based on this new odometry and still work well. I discussed this earlier in the presentation, but again, vision offset is something that might occur a lot at a competition, right? Because if the auto is dependent on vision, then finding the wrong target would mess it up. And this was again apparent for our regional, the Los Angeles North regional, when we caught on to other targets besides the main goal. And so being able to prepare for these, anomalies, and make sure that, we can still come up with a quick and surefire way to have our auto work, right, is really important. And yeah. So I think, I'd like to end today's presentation by, kind of touching upon and discussing safety in developing an auto, right? Autos are really, really, fun to work with, right? There's a lot of, opportunity to create something that might work really well, right? That is really exciting to look at. But at the same time, an auto can be really dangerous if you don't develop it in a safe and contained manner, right? So something that you should always ensure is that before you run an auto, you should make sure that everyone in the room or on the field or anywhere is aware that you are running an auto, right? And they shouldn't be in that location or even near that location, right? You don't want to accidentally hurt a member of your team, or have some other incident happen when you could be a lot more safe with the way you're developing your auto, right? Another really important thing to think about is that you should always check that your robot is absolutely fine before you run an auto. For us, I remember every time we ran an auto, we had to make sure that our turret was calibrated, that our hood was calibrated, and that we were in the exact correct position that we wanted to start our auto at. If any of these things hadn't been checked, right, then the vision tracking on our robot would, for example, fail, right? Our robot may shoot in a random direction. If our turret itself hasn't been calibrated, then we might cause damage to our robot by overextending our turret and turning it in a way it shouldn't be turned because we hadn't reset it, right? So thinking of these measures, right, before you go into an auto is really, really important for the safety of yourself and your team members, and of course your robot too, right? And I'd like to bring up again that testing step by step is really important for the aspect of safety in this regard, because if you accumulate all this error, right, then without just testing a certain part of your auto first, then you might not know, right, what is going to happen with your robot. You don't know where it's going to go, what it's going to do. And that is definitely not a situation you want to ever be in. So testing step by step to know exactly where there might be an error, right? And downscaling your auto work, right? To make sure that, you're not, like going at a very high speed with your robot in an uncontrolled fashion, right, is really important. You want to always make sure that you can disable your robot whenever necessary, and that you don't start your auto out with exaggerated values that may cause it to, like approach another position at a very fast speed, for example, without knowing that your robot can handle that, and it will follow the trajectory, right? So as a whole, it's just really important to think of safety in this way at all times. These are just some resources that you guys can all use if you would, like to see how auto development works on 1678. You should definitely visit our GitHub page at github.com/FRC1678. If you'd like to look at the WPI Lib trajectory tutorial, that is listed here in the WPI Lib documentation. And if you're, curious as to how to properly implement control and you'd like, more depth reading about that, more in-depth reading, then I would highly encourage you all to read Wesley AC's blog on control, because it helps very much with, PID, characterization, etc. Other than that, thank you so much for, listening to today's presentation. If you have any questions, I would love to, answer your questions now. And if you come up with one later, then, please email software@citruscircuits.org for any questions. Thank you so much.
We have a question in the chat. How do you decide what Autons are attainable for early/late regionals? also like how do you avoid running out of time? And what week in the build season do you typically start to test with the physical robot?
Yeah, these are really great questions. Usually we start actually developing our autos the moment we have a viable drivetrain to use, because even if we don't have our mechanisms available, right, our robot mechanisms for shooting or intaking, we want to start developing our paths as fast as possible, right? Um, you know, Developing paths is really important because you want to make sure that your robot is moving in the right direction before you even, try doing things like intaking cells or shooting cells, right? And so having, a drivetrain to simply even work with within a couple of weeks out from the start of build season is really important. I think that we usually start developing most of our autos, just like 3 or 4 weeks, I would say, into build season. In terms of how do you decide what autos are attainable for early and late regionals, I think one of the most important things to discuss in this kind of discussion is, again, what autos do you really want to focus on most, right? Because there will be many contingencies, right? Many different situations that you hope to address when you come up with your autos, but inevitably you will not be able to cover every single situation properly, right? So coming up with a priority list for the autos that you would like to get done before others is really important, because in the end, you'd rather have an auto is consistent and will work every time than one or two or even three autos that may not function at all at competition, right? And to usually pace ourselves, we have a schedule to help ourselves understand um, like at what point in the process we are with our auto development, right? Usually strategy can begin with auto discussion as soon as possible, right? Because they aren't restricted by any actual robot design or fabrication. So after this discussion happens, when we have our drivetrain and we have our mechanisms, it's really important to just get started with it and test as much as possible so we are prepared for competition.
There's another question. You talk about God mode on the robot. What does that mean, and how do you know which commands need this?
So God mode on the robot is simply, a way to say, like doing things through operator input. Like, for example, when you God mode the elevator, you are raising the elevator with operator input instead of, automating a height that the operator simply has to press a button to reach, right? So how do you know what commands need this? You simply I think it's really important that you just discuss with your operator what they're most comfortable with working with, right? So like if you're working from an Xbox controller, right? Like which buttons would they have for their set heights if you automate heights on your elevator? And if they need to go to God mode, which buttons do you think that they would be most comfortable for, right? So just having that discussion with them is really important to understand how exactly you would like to make sure your robot control is as effective as possible.
There don't seem to be any more questions.
All right. If there are no more questions, then thank you all again for listening. And if you have any questions that come up later, then please feel free to ask them at software@citruscircuits.org, and we'd love to get back to you as soon as possible to answer your questions or provide any input or help that we can.
Yeah, and thank you for coming.
Yeah, thank you so much.